k. And then for the next step, it either does the same thing that it did at time k with probability p, or the opposite of what it did at time k with probability 1 minus p. And the position of the elephant at time n plus 1 is given by the position of the elephant at time n plus the steps that it performed at time n plus 1. So when p is 1/2, this simply reduces to the usual random walk, to the simple random walk, because it's just plus or minus 1 steps with probability 1/2, and everything is independent of each other. But when p is not 1/2, then the memory has an influence on the behavior of the elephant. So, for example, if the elephant has already performed n steps, then when it chooses steps, if it remembers a step to the right, then with probability it goes to the right once again, or with probability 1 minus p, it goes to the left. And if it remembers a step to the left, then with probability p, it goes to the left again, or with probability 1 minus p, it goes to the right because it's the opposite. So a bit of
P and Q are different. P and Q.
Excuse me?
At the beginning, you talked about Q, the parameter Q.
Yeah,
and
Q, it's just for the first step, but then it doesn't appear anymore.
Okay.
It's just to signify that the first step might be anything, and that it does not depend on P, but the next steps, the memory depends on P.
Okay.
So, as I said, the elephant random walk was introduced in 2004 by two physicists, and then, well, not that much happened, but in 2013, again, those two physicists, together with some mathematicians, show that in a certain case that I will define later, we find that the elephant random walk, properly normalized, has a limiting random variable that is not Gaussian. So this is the first time that we saw that. Then Bor and Bertoin showed that there is a connection between the elephant random walk and polya-type urns. This is what we are going to use next to prove our results today. And then there was a bit more. So from 2016, a lot more happened on this subject. For example, it was studied using a martingale approach, and some process, some extension of the elephant random walk were introduced, like the shark random swim, which is when the steps are not plus or minus 1, but they are heavy-tailed. So a lot happened in the last few years, and what I wanted to say is that it still continues to be a subject of interest, because as you can see in the last year, there were a lot of paper on this. So this is just a selection to show that there are a lot of different things that are interesting. The mathematician, for example, Jean Bertrand was interested in counting the zeros of the elephant random walk. That is, he wanted to know if the elephant random walk was recurrent or transient in dimension 1, and there is a generalization of the elephant random walk in dimension D. And just last week, some PhD student studied this in dimension 2. So this is the last one I'm going I present here. Other thing that can be interesting is when the memory of the elephant random walk is no longer uniform. Because in the case that we are interested here, we keep the memory uniform, but it's possible to change the memory, and so this has been also studied.
What do you mean by dimension 2? You have two elephants, or the elephant works in a space of dimension 2?
Okay, so in dimension 2, the elephant either does the same thing as what it remembered, or it goes to one of the three other directions of the space.
Okay. That's not means two elephants. Only one.
Only one
elephant.
elephant.
Okay.
Only one elephant, but moving in 2 dimensions.
Okay, thank you.
Okay, so this is to see how the parameter P, that is the memory parameter, has an influence on the behavior of the elephant. So as I said, when P is 1/2, it's just the simple random walk. And when P is small, so that means less than 1/2, then the elephant has a tendency to compensate a lot of what he did. That's because when say that you have performed more step to the right than to the left, then you have, since the probability of choosing either step is uniform, you have a bigger probability of choosing a step to the right, since there are more steps to the right than choosing a step to the left. But since the parameter P is small, you have a bigger probability of doing the opposite of what you remember, that is, of doing the opposite of a step to the right. So the elephant compensates a lot of what he did. And when P is bigger than 1/2, then the elephant tends to do a lot of the same thing. The first step are important, and the elephant tends to go into one direction. And that is until some critical parameter, which is 3/4. And this critical parameter is when the elephant goes to infinity way too fast. Okay, so as I said earlier, the elephant random walk can be studied using a martingale approach. So to do so, the idea is to find a martingale that is related to the position of the elephant random walk at time n. And if this martingale is nice enough, then if you have a result on the martingale, you have result on the elephant random walk. So when we compute the conditional expectation of the position at time n+1 when all the past is given, then we find that it's only depending on the position at time n, so this one, and this, that is a constant depending on n. So this is almost a martingale, because if it was martingale, then we wouldn't have this gamma n here. But luckily, thanks to this, then we can find a martingale that is suitable for the elephant random walk. So this gamma n is just 1 plus a over n, and a is 2p minus 1. So this is a is 2p minus 1. Okay, and so thanks to this computation, we actually find a martingale related to the elephant random walk that is really nice, that has a really nice expression. So the martingale is Mn, and it is this sequence An time the position at time n. The sequence An is completely known. It depends on gamma function, and since we know how gamma function behave at infinity, we know how the sequence behave at infinity. And then since it's a square integrable martingale, we can study it quite easily. This is not what I'm going to do today. And thanks to the study of this martingale, we find that there are 3 regimes of behavior for the elephant random walk. So this is the diffusive regime. So the diffusive regime is when the parameter A is is smaller than 1/2. So remember that A is 2p minus 1. So that means that when P is smaller than 3/4, then we are in the diffusive regime. There is a critical regime that is very close actually to the diffusive regime. That is when A is 1/2. And there is a super diffusive regime. This is what we are interested in our work. And this corresponds to the parameter A being greater than 1/2, which means that the parameter P is bigger than 3/4.
Please, can you give some information why 1/2? Why exactly 1/2? Why the 1/2?
Yes, this comes from the fact that this sequence Vn is so the sequence A, we have AK that is somehow up to a constant n to the power A, 1 over n to the power A, and so the sequence Vn, that is the sum of the sequence AK square, well, it converges when the parameter when 2a is smaller than 1, and it diverges when 2a is bigger than 1, then you have Vn that goes to infinity. And when 2a is smaller than 1, then Vn converges.
Yeah. Thank you.
So thanks to that, it has been possible to obtain a law of large numbers for the elephant random walk. And so this has been done using the martingale approach, but also other approach. So that's why I'm talking about a different paper. So what we are interested here is in here today is that so in the diffusive regime, it's really close to the simple random walk. It's actually the same speed. But in the critical regime, you just have a lower rate of convergence, but it's really close. But in the super diffusive regime, the position of the elephant random walk normalized by n to the power a converges to a random variable. So this is random. And this random variable is what we are interested in our paper, because this random variable is not Gaussian. This was already known. For example, it suffices to compute its moments, and we see that it's not Gaussian with the first 4 moments. But actually, we don't know. We didn't know very much more about this random variable than the fact that it was not Gaussian. We didn't know if it had a density. We didn't know how to compute all of the moments of the random variable. And one thing that we know about this random variable, but it wasn't useful in what interests us, is that so is that in the super diffusive regime, the fluctuation of the random variable of the random walks of the elephant random walk around this random limit are Gaussian, but this doesn't help us to characterize, to know more about the random variable LQ. So this is the main subject of my talk today is who is this random variable. So a first thing that could have been helpful to know more about this random variable is that thanks to their approach and the connection with Polya-Urn, Bohr and Bertrand showed that there was distributional convergence for the elephant random walk, and in the super diffusive regime, well, here we only have t to the power a times LQ, and so this means that we actually don't know more about LQ even with a convergence in the sense of score, because well, this is just the random variable times the time, and so this doesn't give you any information. So we were able to see some histogram of the random variable. The idea is that when so in the super diffusive regime, the first step is important because as I said in the beginning, in the super diffusive regime, the elephant has a tendency to do always the same step. So the first step are really important because the elephant will go in that direction. And so if at first the elephant has as much probability of going to the right than to the left, then it reflects on the law of the limiting random variable, because well, it gives the same as much weight to the right than to the left. And when you have a bigger probability of going, for example, to the left here, then it has a bigger probability of choosing something at the left of the line than the right. But this doesn't give you more information on the random variable. Okay, so now I'm going to explain how we can put elephants in urn. So first, I will briefly recall what is Polya-Urn processes. So the basic of Polya-Urns is you have an urn that is filled with some blue balls and some red balls at the beginning, and then whenever you pick one ball, you watch its color, you put it back, and you add another ball with of the same color. So that's the basic model of Polya-Urn. And there is a first generalization, that is when you pick a ball of some color, you put it back, but then instead of adding just one ball of the same color, you add more than one ball, and possibly of also the other color. So for example, if you pick a red ball, then you put it back and you add A other red ball and B blue balls. And if you pick a blue ball, then you add C red ball and D other blue balls. And all of this is characterized by a matrix that is the replacement eigenvector on the biggest eigenvector with respect to 1/2. So this is a nice generalization. For example, for the elephant random walk, when P is equal to 1, that means whenever you remember a step, you do the same thing. Well, the basic polyhedron model actually models the elephant random walk in that case. And when P equals 0, that is whenever the elephant remembers a step, it does the opposite of what it remembers. Then the polyhedron process, as I introduced just before, when you add a ball of the opposite color whenever you pick a ball, is also the elephant random walk. But the polyhedron process that I introduced just before are not enough to model the elephant. Another generalization, which is instead of having just a replacement matrix, you have random replacement matrix that is that changes at every time. And to understand how the polyhedron behave, instead of studying the replacement matrix, since it's random, you study the mean replacement matrix, that is the expectation of the replacement matrix, because at every time the replacement matrix are independent, but they have the same law. So what is the connection between this model and the elephant random walk? It's that where you say that red balls are step to the right and blue balls are step to the left. And then whenever you pick a ball, you put it back and you add a ball of the same color with probability P or of the opposite color with probability 1 minus P. So if I do a recap of that, that means that whenever you pick a ball of the color red, that means that you remembered a step to the right. But whenever you add a ball of color red, that means that you performed a step to the right. And that's the same with the blue color. Whenever you pick a ball of the blue color, that means that you remembered going left. But whenever you add a ball of the color blue, that means that the elephant performed a step to the left. So in that case, the replacement matrix, the mean replacement matrix is given by this matrix A. And it happened that the ratio of the two eigenvalue actually is A. And if you remember, A is 2p minus 1. So I wrote it back here. And the eigenvector are easily computed. And then, well, you find that the elephant random walk, the position of the elephant random walk at time n has actually the same law as the number of blue ball minus the number of red ball minus the number of blue ball. And because, well, the position of the elephant random walk is thus the number of steps to the right minus the number of steps to the left. So that's the number of red ball minus the number of blue ball. And actually, since here you only have two possibilities, that is going left or going right, well, if you know the time and if you know how many steps to the right you performed, then you know how many steps to the left you performed, because all the steps that weren't to the right were steps to the left. And so that means that actually you only need to know how many red balls in the urn there are at time n, because the number of red ball minus the number of blue ball is just 2 times the number of red ball minus n. Okay, so to study the limit random variable of the elephant random walk, we use that in this paper, in the paper I was talking about. Janssen showed that the Polya urn minus one of its n times one of its eigenvector properly normalized, and once again we find the n to the power a, converges to a random variable times the second eigenvector. So that means that this random variable here, this one here, it's not a vector because this one is a vector, but this is not a vector. And this random variable, we know that it's a random variable and not a constant. We know its expectation, and we know its moment of order 2. And in particular, when in this expression you multiply on the two sides by V2 transpose, then you find that Rn minus Bn, that is the number of red ball minus the number of blue ball, divided by n to the power a, converges almost surely to a random variable, and that's the random variable that was just above. So that means that since this is the elephant random walk, and we knew that Sn on n to the power a converges to LQ, that means that LQ is actually W alpha beta, with alpha and beta properly chosen. Okay, so that means that we are interested in the random variable W. That's the same thing that being interested in the random variable L. So another thing is that we can show that the random variable W, when the urn is started from one red ball and no blue balls, is almost surely the same as the random variable when started from no red ball and one blue ball, minus all of that. So why we can show that? But actually that's because the colors are just fictive, they are exchangeable. So I could say that this is Bn and this is Rn, and then everything is exchanged, and we find that this converges to the same thing. So that's how you can show that. So remember that this is almost L. Then, well, we can first thing that we can show is that the random variable L actually is on the one side just saying if you went to the right or to the left with probability Q or minus Q, and on the other side saying that you went to the to the right at first, because if this is the random variable when, so W is the random variable when started from one red, so red is going to the right. So that means that the first step was a step to the right. Well, you just need to add this random variable that is +1 with probability Q or -1 with probability 1 minus Q to compensate and get all the cases. Okay. So now I'm going to explain what we obtain and how we obtained it. So to do our work, we were strongly inspired by a work of Brigitte Chauvin, Cécile Mayer, and Nicolas Pouyan, where they study the limiting random variable appearing, but in the case of Polya urns with deterministic replacement. That's the first case that I showed. And we wanted to see if the way they studied it could apply to the elephant random walk, that because well, it has a deterministic replacement, so everything doesn't work the same. So the idea is that at first, if we still consider the urn process associated to the elephant random walk, so at first you have one red ball with probability Q, or one blue ball with probability 1 minus Q. And you almost know what you have at time 2. Because if at time 1 you add one blue ball, one red ball, then at time 2 you either have one red ball and you added another red ball, or you have one red ball and you added a blue ball. That means you perform the step to the right, and either you did another step to the right, or you did the opposite and you did the step to the left. And if you at first you had one blue ball, well, at time 2 you have either two blue balls or one red and one blue. So if we say that we fix the first ball, because we want to fix it, because we have W, that's W1, 0, so that's when we start from one red ball, and we have LQ, that's the plus or the minus 1, Z, L, W here. So if we understand W, then we understand the random variable L. So we say that we start from one red ball and we see what happens. So if we start from one red ball, then at time 2, we either have one red ball and another red ball, or we have one red ball and one blue ball. Here it's an example. We say that at time 2 we had one blue ball. So this is time 1, and this is time 2. But then the next is not the time, because we say that every time we pick a ball, then we construct a tree such that every time we pick a ball, that a ball is like a leaf for the tree, and whenever we pick a leaf, then it's not a leaf anymore, because it gives birth to two leaves. That is, it gives birth to itself, so this is this one, and to the one that you add after putting back the one you picked. Okay, so it means that the ball inside the urn are the leaves of the tree that I'm presenting here. So this is the composition of the urn, and this is the composition of the urn at time n equals 5. So n equals 5. So you have this, you have your urn, and if you say that on this side, this is the side 1, and this side, it's the side 2, then you both are either of type 1 or type 2, that means they are either on the first subtree or on the second subtree. Okay, and if you remember that, so this is the type 1 and this is the type 2. Then if you remember how the urn behaves, then at every time you either pick a ball, and the ball you pick, that's either a ball of type 1 or 2 because it's a descendant of the ball of type 1 or 2, because at one time you can go back to either this one or this one. And at every time you add a new ball either in the first subtree or the second subtree. So at every time, either you pick one ball and the ball is either here or here. So that means that at every time, each subtree is only increased by 1, and there is only one of the subtree that has a new leaf. And the way of knowing how many leaves are in each subtree actually is the same thing that looking at a basic polyurn, because, well, if you say that the ball here are of type 1 and the ball here are of type 2, then every time you pick a ball, you add another ball and the ball stays of the same type. So that's like adding a ball of the same color. So the idea is that we want to we want to write the process depending on what happens at time 2, with considering the time. So if we look at our polyurn at time n, started from one red ball, then it's the same thing as looking at a polyurn started from one red ball, but at time, well, the time is the number of balls on this side of the tree. So this is a random time. And it's the same thing as that, plus then you need to consider the other side of the tree, that's this one, or this one. So it's this one if, well, you did the same thing, and that's this random variable. That this random variable here is saying either if you did the same thing, that is, you added a red ball, so it's +1 with probability P, or 0 with probability 1 minus P. And you have to look at it at time, well, the number of ball here, because it's the time. And if you didn't add a red ball, then you added a blue ball. So otherwise, if this one is not equal to 1, then this is not here, and this is equal to 1, and you consider the process when started from a blue ball. And you still consider the time spent here. Okay, so this is the same equation as before. And then we use that, we know how this behaves, because this, so I said that this is the time and that this is the number of balls on each side, and that behaves like a basic polyurn. So the asymptotic of the process is known, and thanks to that, when we use the convergences on both sides, because the convergences are almost sure, so we can do so. Then we find this equation. So here we have a uniform law to the power a. This has the same law as, so this has the same law as this one. this has the same law as this one again, but is independent of this one. This is just saying whether you add a red or a blue ball at time 2. And this is 1 minus this one. And since we know that the W10 is minus W01 almost surely, then we can remove this and replace it with minus this one, minus W10. And so we have a fixed point equation just for W10. So this is the fixed point equation that we have. And then, thanks to this fixed point equation, we can show many things on the random variable W. And that means on the random variable L. Because, for example, when you have this equation, then you have this. You have this. So here we can compute all the moments of the random variable W, because if we have all the moments up to time k, then we have the k plus 1 moment, because here we developed it thanks to the Newton formula. Okay, so this is one of the things we can show. And the other thing that we can show is that the random variable L, Q, admits a bounded and continuous density that is supported by the whole real line. And even more, actually, we can show that the density is of class C infinity. We can show also that the random variable satisfies the Karlman's criterion, and so that it is moment determined. So when you know all the moments, you know the random variable. And we also show that the moment generating function have infinite radius of convergence. And this is the formula for the moment. So this one are obtained thanks to the recurrence, so the fixed point equation. And if you look at this, the decomposition of the moment, actually you see the moment of non-random variables, that is the Mittag-Leffler distribution, random variables that is the Mittag-Leffler distribution. And we can show that there is this Mittag-Leffler, but this is with other techniques that I'm not going to explain today. But so this is here. And I think that's all. Thanks.
Thank you, Lucille, for this nice talk. Are there any questions, please?
I have a question.
Yes.
Thank you very much. It seems that the elephant random walk is not Markovian, since the elephant must memorize all the paths from the beginning. And you established the link between the elephant random walk and the Polia urn, which is actually a Markovian process. How do you explain that you are able to establish a link between two different processes? One is Markovian and the second is not Markovian.
Well, actually, the elephant random walk is a time inhomogeneous Markov chain, just like the polyarion that I consider here. So the idea for the elephant random walk, it's really that since you have only 2 steps possible, the right or the left, when you know how many steps to the right you performed and you know the time, so time inhomogeneous, then you know how the process behaves.
Okay, thank you.
Can I add something?
Yes,
The answer of Lucille is true in dimension 1, but it's not an homogeneous Markov chain in higher dimension.
Yeah.
Indeed, what we see is that we have more information in the polyion. So the polyion, we can do exactly the same thing in higher dimensions, but so we have a link between the elephant random walk and the polyion. And the polyion is still a Markov chain in higher dimension. And what we can see is that indeed the elephant random walk is a transformation of the Yoon process. So the Yoon process is a Markov chain, not the elephant random walk, and it is due to this transformation. I'm not sure to be clear, but this is the link between those two.
Okay, thank you.
Thank you, Hélène. Other questions, please?
Maybe a question, Rafik?
Yes, Mohammed.
For your nice talk. I just want to understand if, I'm not sure, but if there is a kind of phase transition between the dimension 3 and 4, and I did not understand exactly what happened. Because if I understand well in your paper, your approach is still valid in any dimension?
Oh, okay. Yes, actually, we believe that it's still valid in any dimension, but as Hélène explained, in higher dimension, it's way more complicated because, well, in dimension 1,
Yes.
so you have a Markov process, but in dimension in higher dimension, it's not true. And even if the urn is still a Markov process, it's way more complicated to handle. And so the phase transition that we observe is actually it depends on what we are capable to do by hand, or on the computation that we are able to do by hand.
Yes,
Okay.
it is not a real phase transition.
No.
Okay.
We believe that it should work in any dimension, but we aren't able to show it.
Okay. Thank you.
I have a question, if you allow me, Rafik and Lucille.
Yes, Lucille.
Thank you, Lucille, for this nice talk. Could you please go back to the last slide?
Yes.
Okay. Then in the last equation, you have a Laplace transform. You have a Mittag-Leffler function appearing, and we know that this Mittag-Leffler is the Laplace transform related to the inverse of the stable with parameter A. A is between 0 and 1, right?
Yeah. In this case, A is even between 1/2 and 1.
1/2 and 1. Okay, perfect.
Yeah.
Then, is there any chance that your sequence MK corresponds to sequence of moments? Did you try something in this direction?
The sequence MK is the sequence of moments of a random variable that we can identify. It writes as the sum of beta with a random parameter, so it's very hard to understand.
Then, if MK is a moment, the last equation allows you at least to write a factorization in law for L1.
Yeah.
L1 would be, let's say, a random variable x divided by y where y is the power of a positive stable of order A, the power where y is 1 over s to the power A, where s is a stable random variable, positive stable random variable with index A. Then you have at least one factorization, and then you need to focus on the random variable behind MK. But your MK probably L is not positive, right?
No. No.
Then you have at least a factorization. L1 equals x divided by y, where y is something stable, huh? And x will be real.
Well, I don't know about divided, but the factorization that we have is that L is equal to M times some random variable y. And this is the Mittag-Leffler.
Yes, the Mittag-Leffler distribution M actually is 1 over S
okay.
to A, where S is an astable, a positive astable random variable. Besides, then your main concern is the identification of the distribution of L1.
Yeah.
Half of the talk is then you're suggesting that studying a fixed point equation involving the V uniform to the power A, etc., will be a good direction for. There almost nothing in this direction.
I'm sorry, I didn't understand the question.
You simplified L via the study of W. W has an easier fixed point equation.
Yeah, because W has a fixed point equation when where W is the unique solution when L is not.
Then you didn't find anything in the literature for this kind of fixed point equations.
No, actually, we looked into that direction, but everything we find, we always fall in the cases where actually it's the cases where the literature say we don't know.
Yes, it will be probably easier to handle the positive case when everything is positive.
Yes,
but your case is much more intricate, right?
Yeah.
Thank you, Lucille.
Thank you.
And salute to Ellen, who probably forgot who I am.
Not at all.
Okay, L1 is for Q equal 1. It's okay? L1.
Yes. Yes.
Okay, and we cannot have some recursive equation for the moments of LQ in general.
Yes, of course we can. I did not write because since we have actually L1 is the same as W, so since LQ is ZQ times L1, then the moment of ZQ is just plus or minus 1 with probability Q or 1 minus Q. So the moment of ZQ are known. ZQ is independent of ZQ is independent of L1. So we have the moment, if we have the recursive equation for the moment of L1, then we have it for LQ.
Okay. So you have used the connection with polyhedrons to obtain some equation, okay? And after we can send to infinity to obtain some equation about the asymptotic distribution, asymptotic random variable. Okay.
Yes.
And to go to infinity, use some metric or what? What as tools?
Sorry, I didn't understand.
Okay. Use the polyhedrons at every n. You prove that you have some recursive equation with respect to n. Okay. and it tends n to infinity, you obtain some equation where the solution is the limit of your random. So when it goes to infinity, what metric you use to prove that the limit is exactly the fixed point of this operator, of this equation? It's clear or not?
I think, tell me if my answer is completely not the right one, but I think that's because the convergence holds almost surely.
Okay. Okay.
We have the convergence almost surely, and we have a lot of equalities almost surely, so that when n goes to infinity, it still holds even if the equation is in low.
Okay. And why we have only one fixed point of this equation?
Why do we have only one
Yes.
equation? That's because the application is contractant.
Okay. 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 Another question. I think that if we compute directly all the moments of Sn, okay, and we can prove that Sn is bound, the martingale Mn, I think, Mn Sn multiplied by An is bounded in all the space Lp for all P. Okay.
Yes. Yes.
So Mn converges in Lp to L for all P. Okay. And so the moments of all moments of LQ can be obtained as a limit of the moments of Mn.
Yes.
Okay. So if we can obtain a recursive equation, I think the answer is yes. We can obtain a recursive equation with respect to the moments of Mn. We can obtain all the moments of LQ. And so we obtain the distribution of LQ.
What is hard, I think, is to obtain this recursive equation for the moments of Mn, because you know they exist, but actually having them depending on all the other moments is quite hard, I think.
Okay, we can discuss this later, but because I think that we can obtain it without problem. Another general equation. A seed, we consider only one elephant. If we consider two elephants or three or more, and with some assumption about the jumps of this elephant, about the work of this elephant, there are some dependence. Are there some problems or some results in this topic?
I don't think so.
Okay. Okay.
Not with my knowledge.
Okay. Okay. So higher dimension of elephant random walk is with respect to the space and not with respect to the number of elements.
Yes.
Okay.
Yes.
Okay. Okay. Thank you. Are there other questions? I'm very happy to see here with us our friend Hélène Guérin. We have more than 20 years that we have not met. Hi, Hélène. Nice to meet you.
Hi, Rafik.
Other questions, please? Yes,
I have one question. Excuse me, I was late, so I missed the presentation. I'm from signal processing field and wireless communication, and we used a lot of the Markov model and random walk and stuff to model sometimes some type of signals or the channel impulse response and so on. And we may use this kind of models, and we build some predictor and stuff. So my question, did you have any examples where we model some signals or or data or maybe other type of information with this elephant random walk process?
No, that's the thing that is a bit sad to my knowledge. It doesn't model anything in real life.
Mhm. So because assume that I want to model one process, maybe nowadays we have a lot of data from here and from that. And my question, how can we notify the parameters and stuff of of this kind of models in order and how to explore this type of model in practice?
Actually, identifying the parameter P can be done using martingales. We can find an explicit estimator for the parameter P.
Mhm.
So for
Thank
this
you.
type of models, it's okay thanks to martingale.
Mhm. Okay. Merci, thank you.
Okay, the last remark, in your model, you have put your elephant in the air. If you have two elephants, you can put everyone in one air. And things that there are interaction between these two ears, okay? So it reflects the interaction between these two elephants. I think that we can use some results about interacting ears to obtain some results about this model when we have more than one elephant. But the question is this problem interesting in practice or not?
Oh, well, I don't know, but that's not the first time that the question has been asked. So I think that that's an interesting model because a lot of people ask this question.
Okay, okay. So are there other questions, please?
Another question, please, Rafik.
Yes.
Lucille, I would like to ask you if your approach is your approach still valid for variation of this model?
I think that it could work, but it would be much more complicated, and I don't know if we could expect to obtain such so many results, because here what is really nice is that the process, the earn process is Markovian, and some derivation of the elephant random walk cannot be modeled using earn process. So it depends. If the derivation of the elephant random walk can be modeled thanks to an earn process, I think it's okay, and if not, then it shouldn't work.
Okay, well, we have to think about another approach.
Yeah, I think.
Okay, thank you.
Other questions, please. Other questions, please. If not, we have to thank again Dr. Lucille Laulin. Thank you very much, Lucille, for this nice talk.
Thanks.
And hope to see you in 2 weeks.
Yeah,
After
I hope
2 weeks. Bye.
Okay, bye. Thank you.
Thank you. Thank you very much.
Bye, thank you. Bye.
Bye-bye. Bye.
Hélène, tu peux rester.
Oui,
Ça va?
ça va bien et toi?
Ouais, Nabil, tu peux arrêter? Pardon. Excuse-moi.
Comment ça, je peux arrêter?
Tu arrêtes l'enregistrement, s'il te plaît.
Ah, ok.
Parler plus.